tutorial. So we'll look at topologies and topology mappings and something called neighborhood collectives that are useful for these stencil-like computations, for example, and they use process topologies. So it's all connected in some way. So what's the idea here? The basic idea is that your application has some communication patterns. You have some set of processes that communicate with some others and so forth across the whole application. Everyone doesn't communicate with everyone, or not to the same extent. And if you can express this communication pattern in some way, and MPI can map your processes to the underlying hardware in a way such that processes that communicate most frequently are located near each other in some neighborhood, maybe on the same node or on just a single hop away. If that can be done efficiently, then your performance will be better. That's the overall idea. The question is, how do you accomplish that? So first of all, you have to know what your communication pattern is, and in some sense, in some applications, it's quite easy. Like in the stencil, in the life example, it's a 2D mesh. You know that it's nearest neighbor communication, that's easy. In other applications, it might be a graph-based communication structure where some node, you have to draw an actual graph saying who talks to whom, and maybe even a weighted graph indicating the frequency or this amount of communication. So there are two ways you could do this mapping type of stuff. So one way is it could be done up front. If you could tell the MPI, or if you could tell the system before you even run the job that this is my communication pattern in some way. Can you allocate my MPI ranks onto your nodes in some way that this communication happens efficiently? So that kind of method is not widely supported on today's systems. You might have some system specific ways of doing that, but it's not commonly done that way. The second way is using what is known as the topology mapping functions in MPI. So there are two functions. They are called Cartesian topologies and graph topologies. So the basic idea here is given, and you can, when you start your application, MPI just launches it for you the way it typically does, and you get a communicator, MPI com world, that is the ranks in whatever order. Usually, rank 0 will go to the first core or the first node, then 1, 2, 3, in some standard order. But you can create a new communicator using these Cartesian or graph topology communicator creation functions. And in this new communicator, the ranks could be reordered in a way that is a better match for this underlying hardware. So what could happen is that when you start with, the process could be rank 0 in COM world, but after calling the Cartesian or graph topology communicator function, it could end up as rank 4 in a new communicator returned by that function. Your COM world rank doesn't change. So henceforth, if in your program, you just use this new communicator. You no longer use COM world. It's there, but you don't use it. Then you can just act as if you are rank 4 now because you're using that communicator. And if you do this at the very start of the program, right at the beginning, then you don't need to move, you don't need to copy data or anything, right? If you do it sometime later in the program, then it's possible that you've already done some computation based on your old rank as 0 in COM world, and then suddenly you're now rank 4 in some other communicator and you want to start acting as rank 4, you might have to move data around so that you have rank 4's data and so forth. It can get a little complicated. So you want to do this right at the beginning and then just start using that communicator. Some examples showing you why you might want to do this. So let's say this is the graph describing the amount of communication between various MPI ranks. So you could get this after you run an MPI program. You could profile it and figure out how many sends happen between all the ranks. So in this case, there were so many sends between 0 and 3, 0 and 5, 0 and 6, and whatever. Note that nothing between 0 and 1. So 0 and 1 are not communicating in this example, or 2 and 4 are not directly communicating, but it's this pattern. So if you did a naive mapping, if you just ran MPI, perhaps the system would do something like this. It would just put, suppose each node had 2 cores, so it would put rank 0 and 1 on this node, then 2 and 3 out here, and then 4, well, should be 4 and 5 here, 4 and 5 and 6 and 7. So that's the default mapping. But that's not the best for this kind of, so 0 and 1 are on the same node, but they don't even communicate here. So that's a waste. And that you can find other examples, like 6 and 7 are on the same node, but they don't even communicate. So that's a waste. So if you could remap it so that in your new communicator, and this could be done, this can be done by the MPI implementation using some topology mapping library internal to the MPI implementation. If you can express this graph, and we'll see how you express this graph, it could do a different mapping where it'll, the new communicator, this would be rank 0 and 3, and they are communicating quite a bit. So this, in this case, it'll be 0, 3, 1, 2, 5, 6, 4, 7. And with this kind of mapping, you have nodes, the ranks within a node are, they're communicating more. So that's you're using the shared memory within a node for faster. I mean MPI over shared memory for faster communication, and there is less communication between nodes. So this is a way to place or to reorder the ranks so that communication across links and is minimized, and those that communicate are on the same node and so forth. Another similar example is suppose you had this kind of communication topology where 0 communicates with 1 and 3, 3 sends to 2 but doesn't receive from 2, and so forth. And you had this kind of a network topology where the nodes are odd, are 0, 0, 0. They're all at a distance of 1 apart. So if you flip 1 bit, you'll reach somewhere else. So if you flip 1 bit, you reach here. Then the next bit you reach here, and the next bit you reach here. So if you just do a default mapping and you put rank 0, 1, 2, 3 here, you find that 0 needs to communicate with 1 and 3. So how will it go to 1? So it needs to communicate with 3. So this is 0 and 3. But to go to 1, it will follow the same set of links and go here. So this will have 2 sets of messages coming down this link, and others have 1. A better mapping could be something like this, where you place them as 0, 1, 2, 3 here, and here everywhere there's just one message across the link. So 0 communicates with 1, 0 communicates with 3, and 3 communicates with 2. So it's all 1 message per link. So just better utilization of the links. It's a simplified example, but that's the idea. You're utilizing the links better. You're less congestion on the link or shorter distances to travel and so forth. What are these topology functions? They are basically convenience functions. They don't do any communication themselves. You can set up a new communicator, and you can specify whether you want the ranks to be reordered or not. And you want them to be reordered so that the communication is more efficient. That's just a parameter in that function. If you say no to that thing, it won't get reordered, but you get the other convenience features, such as you can, when you set up a Cartesian topology, there is a way to query who is your neighbor in each dimension. So because you need to communicate with your nearest neighbors, but who is your nearest neighbor? So all that you can easily find out using these functions. So there's convenience here. So in MPI 1, right? In MPI 1 itself, there was this notion of process topologies, and it had a Cartesian topology, and it had a graph topology, but that graph topology was not a scalable graph in the sense that at every rank you had to specify the entire communication graph of the whole application. So it was not scalable in the sense that it took too much. On a large system, it will take too much memory just to specify that graph on a million ranks, say. So in those days, they were not thinking in terms of a million ranks in 1993, 1994. So MPI 2 fixed this problem by defining 2 other types of graph communicators where you can specify the graph in a distributed fashion, just like a local information, which makes sense. And MPI 3 added something else. It added communication functions, collective communication functions, that do communication, collective communication, but in a neighborhood defined by the process topology. So say in a Cartesian topology, the neighborhood would be your nearest neighbors in that mesh. So for example, in our 2D mesh life example, if you use the Cartesian topology, and it's there in the code, and you used the neighborhood collective, which are not there in the code, so that can be an exercise. The neighborhood, you can do collective exchange of this. It's a collective communication call, but the data transfer is only within the neighborhood as defined by the graph. And we'll see how you specify that and how it actually works. The advantage is that you're doing a collective operation, so there's room for the implementation to optimize, but it's really a neighborhood, it's really data movement within a neighborhood, not all over the place. And there were some machines where people were trying to do this neighborhood collectives using all-to-all V, and they were getting better. It's a bad way of specifying it, because all-to-all V is like, it's an all-to-all, but with the V you can say 0 for many ranks. So if you're not communicating with all the other processes, only your neighborhood. So you specify 0 for everyone else, and do the all-to-all just in the neighborhood. So it's a very indirect way, but on some system somewhere, I forget which one, I think it was a Cray machine, that they were getting better performance by doing this stencil computation using all-to-all V. But now you don't need to do that. You can use the neighborhood collectives. So let's start with the simplest, the Cartesian topology. The basic function is MPI cart create. You pass an input communicator. You specify the number of dimensions in your topology. So this life could be a 2D topology. It could be any. You could specify 4, 5, 3, whatever. And it's particularly at higher dimensions. It's more useful because otherwise the calculations become more difficult for you if you had to do them by hand. For the 2D, you could even do them by hand because it's just X, Y, and you can somehow figure out who's your neighbor and so forth. 3D and if it's 4D, it'll become more complicated. So this is the number of dimensions in the topology. And this is the actual, this is an array of size n dims where you actually specify how many processes in this dimension are. So it's 16 by 8 by 4 or whatever is your mesh. And we'll see how you even get that number. How do you know what is a good decomposition of the mesh? The next thing is whether your boundary conditions are periodic or not. But what it means is, at the edges of the meshes, do you want to communicate with the neighbor who's actually at the bottom, or you don't want to communicate with anyone on this side? So periodic means if you are at any of the side edges, your neighbor on the empty side has a wrap around, basically. All it means is those convenience functions will return either that neighbor or it will return proc null, depending on what you have chosen. So you can specify true 1 or 0. It's an array of size n dims, and you say 1 or 0 if you want those things to be periodic or not. And reorder means you're allowing the MPI implementation to reorder the ranks. In the new communicator, this process, the calling process, may have a different rank because it's going to do a reorder. And so typically you want to call the reorder because that means you're doing the remapping. If you don't call reorder, then this rank 0 continues to be rank 0. Rank 1 continues to be rank 1 in the new communicator. So the mapping has not changed. It's just that this new communicator will have a Cartesian topology associated with it, and you can do all the query functions. Who is my neighbor in left, right, and what are my coordinates in this mesh, and so forth, which you might need for your calculations in your program. So you typically want to pass reorder equal to 1. So your old communicator is not changed. You get a new one, and now you have to start using the new one if you want to get the benefits of the new topology. So this is an example. Let's say you have a 3-dimensional mesh, a 3-dimensional grid of processes, that is, and it's 5 by 5 by 5. So that's 125 processes arranged as a 5 by 5 by 5. and you want it to be periodic, so you say 1, 1, 1, that is true, which indicates true. That means all the neighbors of the ones on the edges will be the wraparound thing. And then you call cart create with the input communicator, whatever it is. Number of dimensions is 3, and then you pass these arrays. Here you're saying no, don't reorder. You could pass 1 and then it would reorder. This is just an example. When you start an MPI program, you just say MPI exec minus n 240 or whatever number, right? How do you know? How do you know what is a? How do you decompose this, or what is a good? Is it 240? If you want to divide, if you want a 2D mesh out of 240, do you do a 60 times 4 or 40 times 6 or 30 times 8, or what is a good thing? So MPI has some functions to help you with that. So MPI can suggest to you. So you can ask MPI. MPI dims create says, given an input number of nodes, let's say 240, and number of dimensions is 2, it will return in this array a suggested breakup, what it thinks is a good breakup, which may or may not be optimized, but you would like MPI to know what it's doing. So it could suggest 30 times 8, or I guess whatever, 15 times 16 or something. That would be an ideal decomposition according to MPI. You don't have to use it, and there's an additional feature that this dims array is like an in-out array. If you initialize it to some value, one of the dimensions, MPI will try to keep that. So you could say that I have this 240, but I want one of them to be. Well, it's not so useful in a 2-dimensional case. In a 3-dimensional case, you could fix one of the sides to be of a particular size. So MPI will not touch that. It will adjust the other two so that the product still works. So you can those tricks are also there. So yeah, this is what it says. The non-zero entries of dims will not be changed. So MPI will sort of respect the value you provide, and it suggests the other ones so that it still works for the whole thing. So this is a simple example. So the way you can write your program is MPI com size. You get the number of processes in com world. So it's at runtime. You don't know what the user has. The user could have run it on any number of processes. You don't know what they are. At runtime, you find out the number of processes, and then you pass p, the number of processes, and 3 is the number of dimensions to MPI dims create, and it will return this output vector with a suggested decomposition of that into a 3-dimensional grid. And then you call MPI cart create. So you don't even have to figure out how to do it. You call this function, and then you pass the dims from that output of that function as input to cart create, and you get your topology. Typically, you want to do that reorder right at the very beginning. So it's as if you're starting right at that point. So from then on, you could act as rank as the new rank. If you reorder somewhere in the middle, you could have old data that was computed, and then you might have to do a remapping to get it, to get the data in the right place. Once you have created the Cartesian topology, then there are other convenience functions. Then you can query, how many dimensions are there in this Cartesian communicator. So you have to pass that new communicator. So the answer could be 3 or 2 or whatever. Now then you can get the sizes of the dimensions. So these are effectively all the parameters that you pass to MPI cart create. You can query them back. And that's useful if you have passed it to a library who doesn't know who had called the original function. So the library might have to query all this. You can also translate the coordinates to rank and rank to coordinates. So if you have a mesh, then each process has its coordinates in the mesh, starting from 0, 0, and then 0, 1, 0, 2, and 1, 0, and all that. So what does rank 4 correspond to in terms of coordinates? So again, you can do that manually by the size of the total number of processes and the number of processes in X and Y. You can calculate that. It's just a convenience function. And similarly, the reverse translation rank to coordinates. What is rank 7's coordinate? And this one is the other one. What does coordinate 4, 3 correspond to, it will give you. So these are calculations you will do otherwise manually to figure out whom to send data to, basically. The MPI cart shift effectively is to figure out who your neighbor is in one level up, who is your neighbor up, down, left, right, or in the other dimension. It is called, you pass the communicator, you pass the direction, which is, which one is, yeah, so direction is the dimension in the grid. So whether you want to go along the 0th dimension or the 1st or the 2nd, which would be the 3rd dimension, really. And you want to go plus or minus, so you want your neighbor above or below, that kind of stuff. And you can also find who's your neighbor 2 levels up. So it's not your immediate neighbor, but even more than 2, any number. So that's the displacement. You can find your neighbor 1 at any level from there. And then it tells you the source and rank. So this is, again, it can tell you in this grid where you are and where others are, so you can quickly find that rank. Because finally, when you're communicating, you need the absolute rank of that process. The coordinates are not useful in an MPI send or MPI receive. So this is that function. Okay, so that was Cartesian topologies. That's the easier one, basically. the graph topology is harder. That's the general. So if your application is not, it's some unstructured grid with some graph partitioner, and it's a different type of application, then it doesn't fit in this 2D mesh or a 3D mesh model. So then you have to use the graph topology. So this MPI graph create was the one that was originally in MPI 1, and as I said earlier, don't use this one. Use the new functions from MPI 2, which MPI 2.2, which I'm going to talk about. They are the distributed graph functions. So this one, the problem with this one is the information about the graph, which is who's connected to whom. The sources and the destinations for each rank have to be, the whole graph has to be passed on each node. So that's not scalable in the sense that it takes up too much memory. So these arrays will get too large if you're running on a big system. So that's what you want to avoid. So that's why it says don't use this, discourage. So there are 2 new functions in the new interface which allow you to specify the graph in a distributed fashion. Let me jump to that. The first one is it's called MPI dist graph create adjacent, and this is easy to understand. Every rank calls this function and indicates its own connectivity information. So rank 0 will call it and say I am connected to whoever, rank 3, 4, 5, 7, and so much. And then rank 1 will call it and say I'm connected to these, and so forth. So the way it's called is the old communicator. Then the in degree says is the number of processes that communicate with this, because this graph can be a directed graph. I may be sending to some processes and I may be receiving from someone else. So it's not like I have to do both sends and receives with everyone. So you can specify that also. So the sources means it's the list of processes who are communicating with me, and this degree is just the size of this array. So these are all the ones in the graph will be directed to me. And you can also have a weighted graph. So you can, because some of them might be communicating more than others. So you can assign weights to these links. And similarly, the out degree is the number of processes I am communicating to. So this could be the sends, where I am the origin and I'm communicating with others. So this is the number of processes, and this is an array of that size. And you actually list those ranks in this array. And these are the weights for this rank. So it's again a weighted graph for this outbound traffic. Again, there's an MPI info here. This is the hints parameter. Ignore it for now. You can always pass MPI info null. And this one says should MPI reorder the processes or not. And then the result is a new communicator, which is now a communicator with a graph topology, distributed graph topology attached to it. So it's easy to specify because each process just has to specify its own. From the MPI implementations perspective, it's a little harder. It might have to do some communication internally, because since everyone has specified only their own information, it has to make some sense of the whole thing, who is whose neighbors, and so there's some communication internally involved. So one reason might be is if you have done it late in your program, then reordering means that your data might need to be moved now, because suddenly you were computing as if you were rank 2, and now in this new thing you're rank 6, whereas somebody else is thinking is rank 6. So you might need to move. And without this, you can still use all the convenience functions. So if you don't care about performance, you can still, logically, your neighbors could still remain whoever they are. Physically, it's happening over a longer distance and with congestion or whatever. So performance is not good, but you get the convenience feature. So I would typically use 1 and do it early on in the program, so you're not, it doesn't cause any trouble. And so this is an example of how you would specify this graph. So this is a communication graph indicating which process communicates with which process and the direction of the communication also. It doesn't have weights on it. So weights are optional. You could just keep 1, 1, 1 as the weight, so they're all equal. If it was weighted, it would mean it would indicate the amount of communication. So you have to come up with you have to know the communication graph, and MPI doesn't give you a way of finding this, but you could use some tool, performance tool or profiling tool that might give you this information. So rank 0, if you see, rank 0 is sending to rank 3 and to rank 1, and it's not receiving from anybody. Right? It's not receiving from anybody. So the in degree will be 0, and there will be no sources. The sources will be effectively ignored there. There's nobody sending to you. The out degree will be 2, because there are 2 it's sending to, and the destinations are 3 and 1, right? So that's what it would pass to this function. And what would rank 1 do? So in this case, rank 1 is sending to 3 and 4, right? So it has an out degree of 2, and it's receiving from 0, 2, and 4. So its in degree is 3, and its sources are 4, 0, and 2, 0, 4, to whatever order you want. So these are the parameters you feed into the function on the previous page, and that's how you specify your graph. And each process just specifies its own information. So that's what rank 0 would pass. This is what rank 1 would pass, and so on. You don't need to know what the others are passing. MPI will figure that for you. So that's the disk graph create adjacent. There is another one called disk graph create, which is what it says is that you don't need to specify your own information. You can specify any piece of the graph, somebody else's connectivity also, as long as all processes effectively specify the whole graph. So it's a little hard to comprehend that I'm not specifying my own connection. I'm saying how rank 10 might be communicated. So it's just a different way of conveying this graph information. And again, it's up to MPI to optimize it. So it's more flexible than the previous one, where you have to specify your own information. Here, somebody can specify the whole graph, or some subset of processes can specify, as long as the whole graph gets specified. So I won't go into the details of this, because it's just syntax out here. And this is an example of how you would pass that, but that's again just syntax. And now there are, as usual, there are query functions. So once you have associated a graph topology with a communicator, you can find out how many neighbors the calling process has, and how many sources and how many destinations and so forth. And then you can also get the list of who the destinations are and the sources are. So this is useful for libraries. The reason MPI has all these functions where you can set something and then you can also query it is because libraries, when you're in a model where there are many libraries, somebody might have set it and some other library is querying it. You don't know what was set, so it needs to be queried. If you are the sole programmer writing the whole program and you have also set it, you don't need to query it, because you've just set it up there. So, but that's not the case in MPI. It's in a library-based environment. By libraries, I mean FFTW, PETC, whatever. They're libraries that use MPI functionality. Okay. And then you can also test, given a communicator, what is, again, this is for a library. If you call a library with a communicator, how would it know if there was a topology set on it already? So it could query that and then say whether it's a graph, that is the old graph, and that's why there is a sign next to it, don't use it type of thing. Whether it's Cartesian or whether it's the distributed graph, or undefined means there's no, this communicator does not have a topology. Then you will have the undefined. And again, it's to enable libraries to use that. So now these are the slides that Bill mentioned. Bill, you cover this?
I have some more examples where we do see a bigger impact, and it really applies to almost any system. So as we look at these very large systems, as you are mapping the processes onto the network, you're almost guaranteed to have placements that are going to cause congestion. And congestion causes delays effectively in integer multiples. So it can be a big hit fairly quickly, and I'll show an example. Also, for systems that are not dedicated to a single user at a time, so I'm not talking about systems that are shared among thousands of users. They may be shared among a dozen users at a time, most of whom are running some maybe smallish jobs, and a few are running really big ones. It's a very difficult problem to allocate the resources in nice ways. Some people do better than others. The blue gene allocations tend to be nicer than the crays. This is an image of the mapping of a job on our Blue Waters machine, which is a big cray. And so you can see that pretty much things are allocated in lumps, but the lumps are not necessarily next to other lumps, and there's an occasional hole. Those holes are caused by I/O service nodes. In fact, we're moving some of those around to remove some of these holes. But in general, this mapping problem can be pretty difficult, and it has a big impact on the performance. And again, at scale, anything that introduces a performance irregularity will introduce, say, a load balance problem, which will show up as, typically as a delay in MPI. So people are always saying, I need a faster all reduce. And a few people, in fact, need a faster all reduce. Most people need better balanced code. Because what happens is everything's running along, and one process finishes, and it starts as all reduce, and all the other processes finish and start the all reduce. And one process somewhere had been given just a teeny bit of extra data, and everybody has to wait on them. And what you see, measuring the time in an all reduce, is that the all reduce took too long. Now, some libraries give you the option of putting a barrier before the all reduce, and then you can time the barrier. And if that barrier time is not really small, that means that you've got a load imbalance problem. And those imbalances can come from lots of places. So you can say, okay, no, my work is perfectly balanced. There are no problems. You'd say my machine, like the Q, has a separate core on which all of the other services will run, which is false. Most of the other services will run, but not all of them. But even with that, you can get performance variation because of congestion in the network, which is something that we tend not to think about. So remember, this morning, I said you have to think, even with point-to-point, not about just what happens at the endpoints, but what happens in the middle. And so this will be another example. So again, we've got a mesh, and I'm doing some communication, and I'm almost never doing the sort of communication that we have with a point-to-point test, which is I've got some process sending to some other process, I time that, and I get a number. Rather, much more likely that I did a bunch of computation, now I'm going to do some communication, and everybody's going to communicate. So say, for example, that this process has to communicate with that one. Well, you say, well, why is he doing that? Shouldn't he just be communicating from here to here? Well, that's the mapping problem. If the way my communication graph, the way my processes are set up, is not mapped onto my mesh of my physical network, then I will get some communication that doesn't go to the nearest neighbor but goes someplace else. Well, that's still not so bad. The latency's a little longer because of these multiple hops, but the extra time that it takes for each of these hops is relatively small. So why do people worry about those extra hops? This is why. Say this process was sending here. So this process and this process are not even communicating with the same target. But during some of the time that this message, say this message is long enough that there's a bunch of pieces going up here, they are sharing this communication link. And that sharing means that neither of them gets the whole thing, which means that the effective bandwidth on this link to each of the messages is half. So that's what I meant by integer multiples. So my performance, my communication performance has just gone down by a factor of 2 because of that sharing. And on the graph that Rajiv showed you, this edge nowhere appears, right? Because I've got an edge from here to here and an edge from here to here. Right? So it's only by looking at the underlying physical topology that you would see this problem. That's one of the reasons why when you give like Parmenas the task to do this, it doesn't do this because it doesn't have that part of the information. So we'd like to avoid those sorts of effects. Okay, and when you have real communication patterns, you can get these all over the place. In some cases, it is impossible to avoid, so you just have to live with it. And there are strategies that you can take to try to minimize it. So I'll say right now, one obvious strategy is there's nothing wrong with this communication pattern if they weren't both doing it at the same time. So if you can distribute the communication so that you don't have compute phase and a communication phase, you can have an application that's more performance resilient against these sorts of contention. Having said that, it's not necessarily easy to do that. The model of having a compute phase and a communication phase is good. It makes it easy to understand the design, to essentially divide the problem into separable, well-understood pieces. But this is one of the consequences you will have. And if at scale you're starting to run into these sorts of effects, one thing to consider is breaking that model of having sort of synchronous steps. Okay. So I have a test program that I use to look at the performance of a halo exchange. And I want to show you just some results to show you that there is an impact from using the right mapping or the wrong mapping. And you can see a number of other effects too. So for example, when I ran this with 8 neighbors using the I-receive send, so that was the bad thing in the morning, the effective bandwidth was about 660 to 700 megabytes per second. And so this is with CommWorld, and this was with a badly, well, not even, this was with a communicator that was not well mapped. It's not anywhere near as bad as it could be, but there was so it's about a 10% loss in performance just by changing the ordering. But by using I-receives and I-sends, the good thing from this morning, the effective bandwidths were higher. And interestingly enough, the even odd did better. So 1,200 or 1,400 megabytes per second. On the Cray, we had numbers which were much smaller, which is really odd because it has a much faster individual link bandwidth. So I looked at something a little simpler to try to understand what the baseline was. So remember what I said is, this morning again, is having a sense for how fast it should be. So I knew that these numbers were too small. So an interesting thing to look at was, say, I took my stencil, and I know that if everybody is doing the halo exchange, which is what's going on in these tables and these tables, that there's a potential for communication interference, just like in the drawing in the previous slide, that some of those halo exchanges could be sharing a communication link. Blue jeans tend to have pretty nice mappings. The default mapping is pretty good. It's not perfect, but it's pretty good. The Cray's default mapping, I argue, is not so good. And the way I justify that is, what I did was I said, okay, I want to measure a halo exchange without contention. Now, how can I do that? Well, one thing I could think of doing is this. I could say, okay, I'm going to have one process sending it's sending everything it does for its halo exchange. I'm going to have the processes to which it is sending receive, and I'm going to have everybody else keep out of the way. So instead of having a halo exchange like the real situation, I'm going to have one process doing the sending, the process it's sending to receiving, everybody else quiet. So that means that if there's any contention, it's along links shared by that one guy who's sending. So a sort of first level argument is that given other constraints, I would expect the effective bandwidth of that to be about twice what I see with the full thing, because in the full thing I've got data going both ways. I have to deal with data going in and out of the node and so forth. And what we see for BGQ is effectively that. With one sender, I get about 2,800 megabytes per second. With the full halo, I get about 1,400. So that's a pretty close factor of 2. With the Cray, instead of getting a miserable 324 megabytes per second, I get 5.5 gigabytes per second. That's telling me something is wrong. Based on that first picture I showed with that weird sort of mapping of the processes, my conjecture is that in these cases, I'm getting a tremendous amount of interference with communications, the halo exchanges, and here I am not. So this is more sort of similar data. And so this is, so these are now the ratios. So ratio of 2 is about what I predict. So if I see 2, that means that my halo exchange is getting about what I expect. If I see a ratio that's greater than 2, that means that the halo exchange is slower than I expect, right? And so what I've seen in the Crays is progress in the wrong direction. Things have been getting worse as I go from XE3s to 4s to XE6s. And that suggests that you need to look harder at doing this mapping. I will say, while Cray for a long time took what I'll call the ideological position that mapping didn't matter, they have seen the light and they are working on fixing this. But again, when running your application, and either it's on a regular mesh and you're not seeing the right sort of communication performance, or more likely it's on an irregular mesh, then one of the sources of communication problems can be this contention inside the network caused by routes being shared by too much communication. Those are hard to diagnose. However, some of these mapping tricks can help to improve the performance. This is another place where we can say MPI has a nice API to describe how to create the communicator that has the right sort of behavior. Also say that in writing your code, regardless of how that communicator gets constructed, that's the right way to think about doing it. So you should not be writing your code to depend on using CommWorld. And there's a little asterisk on that, which is that some systems are really optimized for CommWorld, so you have to think about that. But you shouldn't depend on that CommWorld. That you can use CommSplit as a way to reorder a communicator. So you split a communicator into one piece with a different ordering of ranks. And then with that reordered ranks, you've effectively moved your processes around. And you can, if you know how to do that, to minimize the communication, you may be able to get much better performance. There are some papers on heuristics to do this. The The full problem is just as NP hard as you think, but just because a problem is NP hard doesn't mean that it's impossible to do anything. Right? So there's quite a few approaches that can give you a pretty good solution without a huge amount of effort. And so using one of those to remap your communicator and then use that is great. And as implementations come up with better implementations of, say, dist graph create, it then becomes very easy to switch from your ad hoc solution or the ad hoc solution you got from your friend to what's in the MPI implementations.
Neighborhood collectives is a new feature in MPI 3, and it is tied to this topology business for collective communication within a neighborhood. As I said earlier, topologies by themselves implement no communication. They are just helper functions and for performance improvement. And the existing collective communications cover only some patterns, and these are usually patterns across the whole system. You know, you do an all gather across the whole machine, or not whole machine, but across the whole communicator at least, and so on, all to all across the whole communicator. And there were requests for collectives for commonly occurring patterns, and a very commonly occurring pattern is this nearest neighbor communication, either a graph-based or a stencil-based. So that this is the solution to that. So there are two functions added in MPI, actually two types of functions. There is a neighborhood all gather, and there's a neighborhood all to all function. And there are variants of that. There's a all gather V and the all to all V and the all to all W, but it's all basically just those two. So again, the neighborhood collective, it corresponds to a cart shift with the displacement equal to 1. So you can communicate only with your nearest neighbors in the Cartesian topology, not at a distance of 2. That cart shift could tell you which were at the distance 2. That makes sense. Again, it's collective in the sense everyone in communicator calls it, even those who may not have neighbors. But the communication is only a process and its neighbors. And then the question is, these are just some details of how is the data actually laid out. When you do a neighborhood all gather, and you get this data from the neighbors, how is it laid out in the receiving buffer in what order? So it's in order of dimensions, and first negative and positive. Negative means the left, and the positive is right in some sense. The minus and plus in that dimension. We'll see an example that makes it clear. Let's say you were doing a neighborhood all gather on this kind of Cartesian topology. So the topology is so 4's neighbors are 1 and 7 and 3 and 5, and we have let's say we have also done the topology with the periodic boundaries. So 0 has neighbors 1 and 3, and also 6 and 2. There's a wrap around. You're going across the edge. So if you in the neighbor what happens in neighborhood all gather, everyone has data to send to the same data to send to its nearest neighbor. So you are getting data from all your nearest neighbors basically, because that's what's happening. So the send, rank 0 has a send buffer, and this gets sent to all its neighbors. So the neighbors are 1 and 2. The 2 is the wraparound, and 3 and 6. 6 is the wraparound. So the send is easy. The receive is there'll be a receive buffer, and where is the data placed? So the data is placed in order of dimension and in the left and right. So the data from the left side will be stored first. That is 2 is the left neighbor. 1 is the right neighbor. So the data from 1 will be stored here, and then the neighbor on the lower side, then 6 will be stored here, and then 3 will be stored here. So that's just a detail of how it gets stored, and just expresses all that in words. So this is how it looks like. It's MPI neighbor all gather. So this is the send buff count data type. So this is the amount of data that gets sent. The same data gets sent to the neighbors. And the receive buff count data type is where the data is stored in the order I mentioned earlier. That's just detail. You can read in the specification how that gets done. So it's easy to understand this, minus the specific detail of where the data is actually placed. And it also has the V and the W versions for flexibility. And there is also a neighborhood all-to-all. What this does is there are distinct data items to send to each process, not one. And again, there is an ordering of the buffer that which part gets sent to which process, similar to how the receive buff is managed. So this is a neighborhood all-to-all. Again, it has the V and W versions for full flexibility. And of course, there are non-blocking collectives, so there are non-blocking neighborhood collectives also. So there is the I neighbor all gather and the I neighbor all to all and the V and W version. As I said, MPI is a complete live. It doesn't cut corners, and it'll have all these variants as well. So just to summarize, topology functions are convenience functions, and to help improve performance, they shouldn't change functionality or will not give you a different answer. So it's something to think about and understand how it might help you. And if nothing else, the convenience features are themselves good. You don't have to do calculations that you would have to do by hand. You wouldn't have to figure out how to divide you're running on 10,000 processes, what is the best 3D mesh that you can get out of 10,000? You can use that DIMS create function, for example. Those kinds of things are also useful. So it's something that you might want to study a bit more if it is useful to you.